Yeah, hello everyone. I'm Sebastian. I'm your guest speaker this week, representing Delft University of Technology. First of all, let me mention that I thought always that Moritz was making these jokes of 100 participants in the lecture hall, but now I can see them really with my own eyes, and I'm really amazed. So thrilled. Thank you for being here, and of course also online to all our participants there. Today's topic are Sobolev embeddings. And roughly speaking, this is the question. So if we know the size of the gradient of u, does this give any information about size or regularity of u itself? Okay, and we already saw some indications if such information can be obtained, namely in lecture 3 you had some exercise that I want to put here as a lemma 10.2. So there we saw we were working in dimension 1 and we had the function u in h1 on R, dimension 1. And then we saw that u has a representative that satisfies the following Hölder estimate. So that the supremum of all x different to y, ux minus uy over x minus y to the 1/2. So just the Hölder 1/2 semi-norm can be controlled by u prime in the L2 norm. Okay, so here we have information on the gradient of u, and this gives us some regularity of u itself. So, and a more general rule of thumb that's in your lecture notes, figure 10.1 is as follows. So we have that u is a L1 log function now in some dimension. And we say that if we know that the gradient of u is an LP Rn, so you see here I take L1 log, this is just to make, so to say, the distributional gradient meaningful, but we have no information on the size of u yet. And then we have 3 cases. So the first case is that, sorry, I want to do other way. P is less than n. This is, so to say, the subcritical case, and there we get higher integrability of u. Then we have here a supercritical case where p is strictly larger than n. This corresponds to this case here. So here we had dimension, or n was 1 and p was 2. There we get Hölder regularity. Yeah, and so then in between is of course missing the case where p is exactly the dimension. And this is called the critical case. Yeah, so in the course of this lecture we will somehow discuss what critical means here. And you see that since we are going to work with p equal to 2, we will have all the 3 cases. So this case here we already saw, the supercritical case. This case will happen exactly in dimension n is equal to 2. And this is the case if the dimension is at least 3. And this will be somehow probably the most important case for us today. Okay, so this is your rule of thumb. And today mainly the focus is p is equal to 2. Okay. And so if you, I hope you all did this exercise that led to this lemma. And there the central idea was we took u, we represented by some representation formula using the fundamental theorem of calculus. And then we could easily conclude this estimate. And yeah, okay, so there's no fundamental theorem of calculus in arbitrary dimension, but at least we have a substitute for this representation formula. So, okay, here somehow use representation formula from fundamental theorem of calculus. And our next goal is generalization for higher dimension. Okay, and this is what I'm going to do in the next lemma. So here we have the lemma 10.3. It reads as follows. So as I wrote here, we want to work with a dimension which is at least 2. And we start with, to obtain these representations with regular functions. So I take a function u in CC infinity on Rn. And then I claim that there's a representation formula for u, namely for all x in Rn, I have the representation that u of x is given as 1 over sigma of n minus 1. So this is the measure of the n minus 1 dimensional sphere at the end, the n minus 1 dimensional sphere. So a sphere in Rn. Okay, so I have this normalizing factor, and then I have an integral over Rn. And then, okay, I want to get representation of u, so somehow u should appear. So let's write us here gradient of u evaluated in y. And then I have a dot product with x minus y over x minus y to the n dy. So it's somehow it's like a convolution integral with this convolution kernel, which is normalized by this dimensional constant. Okay, let us come to the proof. So I take, of course, u as here, x as here, and then I will also need some unit vector. So I take e from the boundary of the unit ball of radius 1. So you could also say it's unit vector, but somehow this perspective, taking something from the sphere, whose measure appears here, somehow more convenient. And then what I do first is I start writing u of x using the normal fundamental theorem of calculus in one dimension. And how can I do this? Yeah, well, I integrate here from 0 to infinity. And then I write here the derivative of the function u evaluated in x plus te. I'm interested in the lower endpoint, so I should here put a minus, and I write here dt. So why is this correct? Let's have a look. So this is just a one-dimensional function. It maps t to this value here. So I can apply the normal fundamental theorem of calculus. I get as result evaluation at the endpoint infinity, but u was a compactly supported function. So if I just take t large enough, this point x plus te will lie outside the support, so this will vanish. And then I have the lower endpoint, so I plug in here for t 0, and then I just get ux. Okay, so lower endpoint cancels out with this minus. So this formula is correct. And then I can use the chain rule. And this will give me a formula like this. So I keep this integral. And I get here by the chain rule gradient of u. This is now evaluated at x plus te. And then I get an inner product with the inner derivative, but the inner derivative is just this vector e dt. Okay, so this looks already a bit similar. So you have here some gradient that is evaluated at something, and you have an inner product with something, but so there's not yet an integral over the whole Rn and so on. So how could we get an integral over the whole Rn? Yeah, well, we could introduce more directions here. So we just fixed one direction. We want an integral over the whole Rn. So let's introduce all directions. And how can we do it? Well, we we average this identity that we derived here over the full sphere. So the left-hand side doesn't depend on E, so it will not be affected by averaging, but the right-hand side will be. So let's write it here. Average over E gives me on the left-hand side still Ux. On the right-hand side, I get here an average integral over, so let's write it directly in this way. So I get 1 over sigma n minus 1 times an integral over the sphere. Okay, so this is just this averaging that doesn't affect the left-hand side. And the rest I copy to infinity, gradient u evaluated in x plus te dot e dt d sigma of e. And now what I want to do next is I want to swap the order of the integrals so that I can go back to an Rn integral using polar coordinates. So this is, of course, I can just apply Fubini because the u is regular and compactly supported. So okay, I will be able to interchange these two and these two. And as I said, I want to use a substitution to get polar coordinates. So to make my life a bit easier, I will directly rewrite this E a bit. So I write, I want to do a substitution with this. So I write here also TE. Then when I want to use polar coordinates, I will need something like t to the n minus 1 here. So I have to compensate this t to the n minus 1 and this t. So I write here t to the n. Okay, so maybe let's copy again this line with all the modifications that we did. We have u of x is minus 1 over sigma n minus 1. Then we get this integral now 0 infinity. Here we get this integral over the sphere, 0, 1. The rest I copy. Gradient of u of x plus te, inner product, te over t to the n. Then here I also swap the order. So let's write here the sigma of e. And here this t to the n minus 1 dt. We want to use here a substitution, so we define this as z, use polar coordinates. So this gives us minus 1 over sigma n minus 1, integral over Rn. Here I get gradient of u evaluated at x plus z, and our product with z over tn dz. So this cancels out in virtue of the change of coordinates. And now it looks already quite similar to the lemma that we want to show. It just remains to do a last substitution. So this x plus z we define as y and do this substitution. It gives us first minus sigma to the n minus 1 integral over Rn. Now here I really just get a gradient of u evaluated in y. Then here I get, so z becomes then y minus x over x minus y to the n dy. Now I can do some cosmetics. I cancel this minus, swap here the order, x minus y. And this is exactly the representation that we wanted to show. Okay. So the idea is somehow we want to consider this as a convolution type integral where this is somehow related to the kernel of this convolution operator and gradient u is the argument. And I want to do a definition first of the so-called Riesz potential, and then we will somehow see how it relates to this representation formula. So let's write it down. Definition 10.4. Okay, so we take a function f from Rn to the complex numbers, and we assume just that it's measurable. Okay, so of course, if we for this object that we're going to introduce, if we want to show really properties of it, we will need more than measurable, but measurable is enough to at least write down a meaningful definition. Okay, so we want to define an object jf. So it's an operator j that acts on f, and we do this pointwise. So in a point x, we define it by the integral. Well, it's essentially this integral here, so it's 1 over sigma n minus 1 integral over Rn f in y. The only difference that I do is I don't take this kernel here, which has a sign, but I take, so to say, its positive version. So I will also apply like an absolute value on the whole expression, and then this will give me an x minus y to the n minus 1 dy. Now you might ask, okay, why is this even defined? Why does the integral converge? Well, for general f, it will not converge, at least not in every point. So we define this just whenever defined. Yeah, so this function j of x is only defined in x where the right-hand side makes sense, but we will later restrict the class of f's that we investigate, and there we'll see that the integral will in fact exist for sufficiently many x. Okay, so this mapping is called the Riesz potential. And it's called a potential. We will see this later. Somehow we have an integral operator that acts on f, and it's an integral operator that will make things better. So potential is usually something which takes an object and makes it better and not worse. Okay. So how is this related to the representation formula that we had before? I make here such lines so that you see that the definition is finished. So we get from lemma 10.3, was just this lemma that we had here. We can take u of x from this class of CC infinity functions. We apply absolute value. Okay, so this will give me 1 over sigma n minus 1 integral of Rn f of y, gradient u of y, and then the rest just gives me this kernel, so x minus y n minus 1 dy, and this is by the definition from just above, definition 10.4. This is just j applied to absolute value of gradient of u evaluated of x. So we see that at least for this class of regular functions, using this Riesz potential, we can get a bound of u pointwise by a bound of this Riesz potential applied to the gradient u pointwise. And the hope is somehow that if we can show mapping properties for this j, it will translate LP information for the gradient of u to some, say, LQ information on Q itself. Okay. Let's go to the next blackboard. Yeah, so I said we are interested in these LP-LQ mapping properties of J. And first of all, we can make some, let's say, sanity checks or calculations which indicate for which P and Q this might even be possible. Yeah, so maybe we can already get a good guess on which P's and Q's we should concentrate our study. Okay, so how does it work? What to expect? We take just some stretching, another question. We take numbers P and Q in 1 to infinity. Yeah, but so if you are not stretching but have questions, just interrupt me, okay? So we take two numbers P and Q. We are interested in the question, does J map LP Rn to LQ Rn? And to see if this is possible for certain P's and Q's, we do the following construction. So we had for instance, when we studied the Fourier transform, we worked with these dilations. So we somehow had that sigma t of phi evaluated at x was this function phi, but not evaluated at x, but at tx for all t larger than 1. So these were these dilations. We can work with a family of dilations in the estimate that such a boundness would give to find for which P's and Q's this mapping property might actually be possible. So this is called the scaling argument, and it's quite popular in establishing estimates. Okay. So what happens? We take some function phi from CC infinity Rn. So this in particular, this function I can plug into the Riesz potential. It will give me a well-defined, meaningful value. And for dilation, I can do the same. So this is somehow a good class if I want to test the Riesz potential without knowing anything about it. I should exclude the case that the function is 0, because then, okay, on 0 I will somehow not get any trouble estimating this object. I mean, if you plug in there the 0 function, the Riesz potential is also 0, and then you have all PQ mapping properties that you want. So okay, but if I take such a phi, then I can ask myself, so what happens if I calculate the Riesz potential not of phi, but of this dilation of phi? And for this, so you can just, as an exercise, write it down using basic substitutions. But you will find that this is exactly t to the minus 1 times the dilation applied to j phi. So you see, j and this dilation, they don't directly commute. They only commute up to this additional blow-up factor that comes from the scaling. Okay, so, and now we want to plug in this quantity here into an LQ norm. So let's do it. Right here, j delta t phi in LQ norm. And if I assume that I have this, so let's write here maybe assume J mapping property will give me a bound against delta t of phi in LP norm. And then of course for this dilation of an LP norm I can again directly compute what it gives me. So the value of this is t to the minus n over p times the p norm of phi. So this is again just you do the obvious substitution. Okay, and on the left hand side I first want to use this identity. So this comes from here. Then I get here delta t j phi in q norm with a factor t to the minus 1. And okay, I didn't do my spacing well, but let's write below. So okay, here we have again a dilation of some function. The function is now j of phi and not phi. So as above here, I get as this is t to the minus 1 minus n over q times j phi in q norm. Okay, so what does it help? Well, we said that okay, phi is not 0, So this is some number which is strictly positive, and it's independent of t. Here the same. So what we have shown here is it's somehow an estimate. This power of t is less than a constant times this power of t, but it holds for all t. So if the power of t here and the power of t here don't coincide, we can either send t to 0 or we can send it to infinity, and the left hand side will blow up. Okay? So can only hold if -1 minus n over q is equal to minus n over p. Okay, and then we can rewrite a bit. So first we multiply it by -1, and then divide it by n. Then we get. I also want. So in the end, I want to get some formula for 1 over q. So okay, -1 gives me a plus, plus, plus. Then I put this +1 to the other side. Gives me. We do it a bit iteratively. Okay, let's first do it like this. Okay, here we get minus n over q is equal to n over p minus 1. Then we also divide by n. So this becomes a 1. This becomes a 1. This becomes 1 over n. Okay, so we can have LP to LQ boundedness for J only if Q is given, or 1 over Q is given by this relation, which only depends on P and dimension. So this is first observation. Second observation is, we said here that, okay, P and Q, they are both numbers in 1 to infinity. So we must have that P is at most n. Because if P is larger than n, then you get here something negative. Here you have something positive, so that can also not be. So we have this, and P is at most n. Okay, and this number Q here, we want to give it has a special role, so we'll give it a special name. This is content of definition 10.5. So first we take P up to n, but n excluded. And then we set a number P upper star via n times P over n minus P. And you will see that if you take 1 over P upper star, it will be exactly this number Q here. Okay, so this is the Sobolev conjugate of P. And for convenience, we'll also define this number P upper star in the case that P is equal to n. So if P is equal to n, we define P upper star simply as infinity. So this is also, if you were using this formula, then you get here something divided by 0, and this, okay, by the right convention, this would somehow also be infinity. But we don't use these conventions, we just directly write it. P upper star is, in the case P is equal to n, is infinity. Okay. So somehow what have we learned up to now? If something will work, then that J is a bounded mapping from LP to LP upper star. Okay, maybe let's write it down. If ever, then J from LP Rn to LP upper star Rn. And the task is, okay, this would be reasonable, this is possible. Now the question is, do we get it, and do we get it for all these p's here? So really from 1 to 1 included to n included. Okay, so next I will switch to this blackboard and write the central result that we're going to prove in this lecture. So I will somehow, so this was definition 10.5. I will now directly jump to theorem 10.7. There's some preparatory lemma in between that we will do afterwards. Just as some motivation, I show you the theorem before. So this is called the Hardy-Littlewood-Sobolev inequality. Okay, and so the first two names, they can give you some indication why we treat these results in lecture 10 and not back then in, I don't know what it was, lecture 3 or lecture 4, where we first treated Sobolev spaces. But we will really need this result from real variable analysis that we only dealt with in the last lecture, lecture 9. And Sobolev, of course, comes from the gradient that is involved. Okay, so what does it tell? We take some p in the open interval 1 to n. So here you can also already see a bit. So I didn't write down any restriction on dimension, but if the dimension is 1, then you have the open interval from 1 to 1. So there's no p in it. So we get no assertion about dimension 1 from this result. And you also see that if the dimension is 2, then I just exclude the case p equal to 2, and this somehow reflects also this criticality that we wrote up here. So I said that in dimension 2, p equal to 2 is just critical, and this is just what you see in this formulation of the Hardy-Littlewood-Sobolev inequality. Okay, then we also take some f in LP Rn. So also you should keep a bit track of regularity of the functions that we should consider. So first I had my representation. It was just for CC infinity functions. Then I defined here the Riesz potential for measurable functions. Now I work with p integrable functions. So somehow we work with many different classes of measurable functions, but somehow necessary to sometimes be more restrictive with regularity and sometimes be a bit more general with these formulations. Okay, so what happens then? Then I have the following. So two assertions. First, we wrote down the Riesz potential jfx whenever x existed. And I claim here that jf converges absolutely for almost every x. Okay, so in particular, when I work on LP, the Riesz potential gives me an almost everywhere defined measurable function. And then the second assertion is that there exists a constant c, which only depends on n and p, such that we have the following estimate. We have that jf in p upper star norm is controlled by this constant times f in the p norm. Okay, so somehow when you compare with this, I said, yeah, well, this is possible, but do we get it for all p for which this is possible? And the answer is almost. So the possible p that we calculated there would also include these endpoints 1 and n, so the closed interval, but we have to throw away these critical case or endpoints of what is possible, but then we really get the best possible mapping properties of J that we could hope for. Okay, so this is the main result that we want to prove today. And as preparation, we will have some some lemma, or maybe let us have a look back on this representation here. So I said the least potential is somehow a convolution with some kernel, and you will see that this kernel is somehow a singular kernel around 0. So we'll need to do some fine arguments to control the singularity near 0. This is the on-diagonal part, and this will be the part that we deal with in the first preparatory lemma. And then we also have some off-diagonal part, which somehow doesn't pose the difficulties of the same grade as this on-diagonal part. But somehow in the end we have to combine both parts so that what we get from this off-diagonal part, which is the less complicated one, at least matches the results that I get on the on-diagonal part. Okay. So let's treat this on-diagonal part. Lemma 10.6. So we take f in L1 log Rn. So I still don't get enough in introducing new classes of functions f. So this is now the fourth possibility that we have. We take some point x in Rn, and we take some r positive, and then I want to estimate the least potential, but just in some ball around 0. So just some ball of some radius that we have to see what is a good choice for the diagonal part. Okay. So here integral sign, I write fy over x minus y n minus 1 dy. If I write here Rn, this is just the least potential, but I only write the ball bxr. So I just take something around the singularity of this convolution kernel and want to estimate this. And what do I get? I get some constants. I get 2 to the n dimensional constant. I get here omega n. So omega n is the volume of the unit ball. Volume of B01. Okay, also dimensional constant. Then I get here more interesting r. This is the radius of this ball here. And I get the Hardy-Littlewood maximal operator evaluated in this middle point of the ball, x. So and this estimate is really for all x in Rn. Okay. Let's do the proof. So I have this ball here, and I somehow want to introduce or get some more information on this kernel here. So I should not work with the full ball, but I should somehow decompose it so that from the different parts of the decomposition, they will give me some information on the kernel. Okay? So I write bxr is the union for j larger than 0 of some balls that I have to introduce, namely bj without bj plus 1. What are these bj's? Where bj is defined as a ball around x. The radius also appears, but I introduce some additional scaling 2 to the minus j. Okay, so let's do some sanity checks. When I take j is equal to 0, then I get here just the ball bxr. And in every step, I somehow remove the ball of the next generation. And so this I get a disjoint decomposition. Maybe we can make I brought all these colors but didn't use them so far, so let's make a small picture. So in dimension 1, this would look like this. So I have here my ball in dimension 1, it's just an interval. So yeah, here is 0 and here is r. And then in the first generation, I have to remove a ball of radius r/2. So right here r/2. Here's minus r/2. So in the first generation, I get this shell. In the next generation, here I have r/4. Here the same. Okay, then I get this. Yeah, it's not so well drawn, but you somehow see that this should be double size than this, and I would here introduce something which is again half size, and so like this I exhaust the full ball by some shells which get smaller and smaller in a dyadic way. Okay, and why is this helpful? Let's write again the integral that we want to estimate. So we had here bxr fy over x minus y n minus 1 dy. We write it with this decomposition, so it gives us sum over j positive. And I get here bj without bj plus 1 fy over x minus y n minus y dy. So what is now this extra information on this kernel here? Well, okay, this is 1 over this, so I should get a lower bound for distance of x to y to get an upper bound for 1 over this quantity. And the lower bound for x minus y comes from removing this ball. So I know that so x is the midpoint of this ball here. Yeah, it was written here. But y is not in this ball. So somehow I get when y comes from this thing, it gives me that x minus y is at least 2 to the minus j plus 1 times r. And this I plug in this kernel estimate. Then I get that the whole expression is less than sum over j. So here I can, after I use this information, I can throw this away. So I will write here just bj. Here I copy this fy dy. And now here I use this estimate. So this will give me 2 to the minus j plus 1 n minus y. Okay? And now in the next step, so you see, in the end, we need here some maximal operator. A maximal operator was always defined. We take the average over some ball. Now here we have an integral over some ball. We are lacking some average. So and also this does not depend on y anymore, so we can pull it out. So here we really just have integral over fy. Integral over fy dy. Here bj. I want to make this a maximal function. So I introduce here some average. That's maybe a short reminder for our calculation. What is the measure of bj? It's just the measure of the unit ball times the radius of this ball to the n. So I get here 2 to the minus jn rn. This is, I divide it by this measure here. So I have to compensate for it. So for sure, when I divide here by wn, I have to multiply here by w to the n. And for these latter factors, we will see what from these factors what we find in here. So here I have 2 to the minus j n. So this is there. Jn will give me this. I'm lacking some small typo. So sorry, I forgot to write here this r to the n. Yeah, so this r to the n comes from here, of course. Okay, so this r to the n that's not r to the n, it's of course r to the n minus 1. Yeah, so here we have, here's the r and here's the n to the minus 1, so this is r to the minus 1. Then somewhere here we can maybe write here to the minus 1 r. So this is this. So we see that everything, these two things, we already defined in this expression here. And we just have to see what remains. So what remains is this r here. And then also some powers. So we have here j positive. And then I'm lacking this 2 to the, so I had this jn. Then I'm missing 2 to the minus j. And then I should get, maybe I write it here, this 2 to the n minus 1. Okay. Hope this is correct now, but looks good. Okay, so, and as I said before, this object here can just by definition of the maximal function be controlled by mf evaluated of x. Yeah, so these bj's, they are all balls centered in x, so by definition this is controlled by mfx. So in particular, we can pull it out of the sum over these j's. Then I simply calculate this geometric sum, gives me 2. So this 2 will cancel out with this 2 to the minus 1. And so in the end, I remain with 2 to the n wn r mf of x. Let's compare. Was it what I claimed? 2n wn r mf. Check. Okay. Yeah, maybe then we do our break now, and after the break we come to the proof of Theorem 10.7. Okay. So let's get back to our Hardy-Littlewood Sobolev inequality. So what did we want to show? We said that we take some p, which in the open interval of exponents for which we could expect LP to LQ mapping properties for the Rees potential J. We took this function f from LP, and then we claimed that on the one hand, we really get that the Rees potential gives almost everywhere defined measurable function, so the defining interval converges absolutely, and we also get this mapping property from LP to LP prime, where LP prime was the upper Sobolev conjugate. And we just had this preparatory lemma where we just estimated a local on-diagonal part, which is somehow the more complicated of the two parts that we have to estimate. Now we want to bring everything together. So proof of Theorem 10.7. Yeah, 10.7. Okay, so first of all, we want to make some reductions. So what is quite clear is that if I take JF and I'm interested in its size, so I plug here absolute values, then I can just in the definition of the Rees potential use the triangle inequality to find that this is dominated by J applied to the absolute value of F. So this tells me that I can work with non-negative functions. And secondly, this we already mentioned when we discussed this scaling argument. We can, maybe I make here a dot and then the next dot. So we can assume that f is non-trivial. So we say that, so we already said we take it non-negative, and we also don't want it to be 0 everywhere. So this tells us that we are strictly positive on set of positive measure. Yeah, so this is just what it means, that you are non-negative everywhere and you are not almost everywhere 0. Then you must be strictly positive on some set of positive measure. And why is this helpful? This implies in particular that the maximal function mf of x is strictly positive for all x. Yeah, why is this the case? You simply, you fix some point x and you just take some ball that is large enough to contain the set of positive measure. Then you integrate a strictly positive function over the set. Then you before have this normalizing factor, which makes, maybe you start with something very small, then you make it even smaller, but nevertheless you will get something which is strictly larger than 0. So this lower bound, of course, depends on x, but it's not important. It's just for us, it's important that we know that this number is never 0. Okay, so with these preparations, we take our, maybe I just write like this, so I always estimate j applied to the absolute value of f. And what I want to do first is I want to split it into these diagonal and off-diagonal parts. So right here, bxr for, okay, I write down, then I comment on this r. bxr of fy dy over this x minus y to the n minus 1 plus the remaining part, so same integrand, fy over x minus y n minus 1 dy, and then I have here Rn without the ball bxr. So and for this local on-diagonal part, we had this preparatory lemma from before, and there we said we can have it for all r positive. And somehow this r positive gives us some degree of freedom. So for the moment, we just want to say, okay, we take some positive r, then we estimate this part by the lemma from before. We will calculate what happens out here, and then in the end we want to use this degree of freedom r to somehow get the best possible result that we can get from such a splitting. Okay, so right now, let r positive some degree of freedom. Okay, what do I get then? So I use the splitting. Jf, maybe I should write here also x. J of fx, smaller than, we had these two parts. And for the first part, we just used this lemma 10.6 that we proved before the break. So this gives us an estimate against 2n, omega n, r, and the maximal function evaluated on f absolute value of x. And then I get this second part. This I will just copy. Rn without bxr, and then here I have fy over x minus y n minus 1 dy. And as I said, so we want to estimate the second part now. We want to see, okay, what can we somehow get out of it? And in the end, we want to choose r in a way so that the sum of both things will be the best possible result that we can have. So we will somehow use this R to optimize this additive inequality that we will obtain. Okay. So let's continue with this. And what do we have here? So we have an integral, and it's in fact an integral over the product of two functions. One part is this f absolute value, and then we have a second function, this kernel here. And what do we do usually when we have an integral over a product of functions? We use Hölder. Okay, and how should we use Hölder? Yeah, well, in the end, I want to get an estimate against f in the LP norm. So maybe it's good to put in Hölder an LP norm on f and a p prime norm on this kernel here. Okay, so this is then less than the integral over Rn without bxr fyp dy 1 over p, and then here I get integral over Rn bxr, and here I just keep the kernel, so then I have x minus y to the minus n plus 1, and the whole thing times p prime 1 over p prime. Yeah, okay, it's just the Hölder conjugate, I mean, we know. dy 1 over p prime. Okay, so here this is the LP norm of f over a smaller set. So I, instead of Rn, I remove this ball. I don't care, I just include it. So then I get for the first part an estimate against f in LP norm over the whole Rn. And the second part, when we look at it, it looks really much like we want to use polar coordinates. So let's do this. So first of all, we can use a translation. So here we excluded a ball around x, but also here we have x minus y. So we can just replace this x by a 0, and then here just write y. Okay, nothing happened. Now we want to introduce polar coordinates. And these polar coordinates, will give us an integral from 0 to infinity. And then I get here, this is, let's say just, so I substitute t is equal to the absolute value of y. Then I get from here t to the minus n plus 1 p prime. Then I get, additionally, from using polar coordinates, I get some extra factors of t. So I will write here plus n. Normally it's n minus 1. This minus 1 I will put into the measure, so I will write it against the H measure. Okay, 1 over p prime. This is just this expression in polar coordinates. Now the question is, major mistake. So here it's of course not from 0 to infinity, but it's from r to infinity. Yeah, so we exclude the ball around 0 of radius r, so we should only start integrating from r. Yeah. So if we have such powers and would integrate from 0 to infinity, we are of course dead either in 0 or in infinity. But here we just have, or could have, a singularity in infinity, and we want to rule this out. So we should see if this exponent here, if this is strictly negative. So if this is strictly negative, then we have here this additional t to the minus 1, so it will give us integrability at infinity. Okay, so how did I want to calculate this? So we investigate this number here, and I write minus n plus 1, and this p prime I want to write as p over p minus 1. That's correct, right? Yeah. I'm really good in writing stuff in 1 over p notation, but not the actual number. Yeah, so I have to look here what the inverse of 1 over p prime is. Okay, what did I do here? Sorry. Okay. Plus n. And then we can essentially just compute it. Okay. So this gives us, we want to write as p over p minus 1. Then we get here np minus n. This factor here gives us minus np minus p. So in the end we have here some mistake. What did I write here? Minus n minus p. Sorry. So here I had n times p minus 1 gives np minus n. And then here p minus 1 times this. And this times this gives me. This cancels out. Minus. What did I write here? Which one? This you mean? No. I just want this. Okay, did I copy it correctly? N minus n. Here's the mistake. Sorry, what did I write here? Okay, so this is minus 1. This is minus 1. Yeah, so here we had n minus 1. So here n minus 1, here n minus 1, here n minus 1. And I get here a plus n, and then everything is good. Yeah, sorry for that. So this cancels out with this. In the end, I remain with n minus p over p minus 1. Still weird. P minus n. So in the end, we should have minus n minus 1. P minus 1, this was correct. Minus p, pn. Oh, is this correct? Okay, modular science should be the other way around. Exercise for you, p minus n. And then you really get that this is strictly negative. Yeah. Okay, so up to some calculation difficulties, we will get here f in p norm, and then we get here r to the, this exponent, p minus n over p minus 1, everything multiplied by 1 over p prime, and 1 over p prime is p minus 1 over p. Okay, and we can cancel this out with this. And we just remain with f in p norm, and then here r to the p minus, okay, I can even write here, so p over p is 1 minus n over p. So this is what I get for the off-diagonal part. Now we can combine both estimates that we had. Okay, so implies that j of absolute value of f in x is estimated. I throw away all constants, but we saw that there are only constants that depend on dimension on P. And then I had for the on-diagonal part, we had R times MF evaluated at X plus what we had right now. So this was F and P norm times R to the 1 minus N over P. Okay. And now we want to use our degree of freedom that we had from R. And how do we want to do it? Yeah, well, here we have the sum of two things. And there will be, this estimate will become optimal if we balance these two things. So if we say that this quantity is equal to this quantity. Yeah, so before, if we don't balance them, one will be larger than the other, and so we get a non-optimal constant or non-optimal estimate. But if we balance them and say this equal to this, then we will get the best estimate that we can get out of it. And how do we do it? So we want that R MF of X is equal to F and P norm R to the 1 minus N over P. This is equivalent to, so first of all, I maybe sort R's to the one side and the rest to the other side. So this will give me, so this minus this R gives me R to the minus N over P is equal to MF of X, and then this I have to bring to the other side, gives me F in P norm to the minus 1. Okay, then I can remove this power. So this is equivalent to, and here now you see, so I want to in particular take the whole identity to the minus 1, and for this I need that this is non-zero and this is non-zero. So this is non-zero because we work with a non-trivial F, and this is non-zero by this reduction that we had at the beginning. So I can indeed take everything to the minus 1, and then I get here R is equal to MFX to the so minus P over N, and here I get F to the P over N. Okay, let's see if so far I didn't mess up. P over N. Okay, so far it looks good. Then we should plug this back into this identity. Then I get J Fx is controlled by, so I balance both, so I can just take this R and plug it into this first term, say. Then I get MF of X to which power? Well, I get this power 1 that I have here, 1 minus P over N, and I get this in P norm to the P over N. Okay, so this is the pointwise bound that we get for the Rees potential. And in the end, we want an estimate of the Rees potential in the P star norm. So we apply the P star norm to this pointwise bound. Okay, implies JF in P upper star norm is controlled by, this is just a number, so I can pull it out of the norm. I get F in P norm to the P minus N, and then here I can maybe write the P star norm out. So I have here an integral over Rn, then I have here MF of X to the power minus 1 minus P over N. and all this times p upper star dx 1 over p upper star. Now we should calculate this exponent. So I was clever enough not to erase the definition of p upper star. So okay, let's write it here maybe. So I have 1 minus p over n times np over n minus p. But this I can write, so I just expand here n, and then this cancels out with this cancels out with this, so I just get p. Yeah, it's always magic with the exponents. Okay, so what do we have here? So in fact, here I have like an LP norm of the maximal function. This p is taken strict larger than 1 and strict less than infinity, so we can use the LP boundness of the maximal function that we discussed in lecture 9. So we get here a bound. Let's give the correct number. So this is Theorem 9.8. 9.8. This I copy. P over n. Then I get here the p norm of f to the power p over p upper star. Okay, then we have to do last calculation. So yeah, just write it out. So I mean, in the beginning, I even gave you the definition of 1 over p upper star. It was just this quantity q that we had here. So we said that 1 over p upper star is given by 1 over p minus 1 over n. Okay? So this is this 1 over p upper star. Then I want to multiply it by p. Okay, this gives me 1 minus p over n. Okay, so here I have p norm p to the n, another p norm 1 minus p over n. Then I cancel this out with this, and I just remain with the LP norm of f. Okay, so this was indeed what we claimed in the result. Yeah, so we have this estimate. Maybe just so about these restrictions that we had here for the p's. So I already discussed a bit why we cannot allow p equal to 1. If we have p equal to 1, we cannot use boundness of the maximal function in the last step. Maybe let's have a look why we can, or where the proof would fail if we have p is equal to n. For instance, you would get problems in this balancing argument here, right? Because if p is equal to n, then I get here r to the 1 minus 1, so this r cancels out. So here you don't have a power of r to balance. What you can do is you can take this power r to make this first term equal to the second term, so you would get a bound of the Rees potential by a constant. But if you plug in just a constant into this LP upper star norm, yeah, okay, it doesn't help you anything. So you really need some power of r here, so that in the end you get a pointwise bound by something which involves the maximal operator, so that you can hope for these LP upper star bounds. Yeah, so there you can somehow see from the proof by you have to include these both endpoints from the consideration. Okay, now we show this, and it was our last proof for today. Now we'll do a lot of corollaries. So it's time to harvest what we worked for. So the first corollary 10.8. this is about this lemma 10.3 that we had in the beginning. So I copied it to you again here. So this was this thing where we said, okay, if we start with a really regular function u, we take it from C0 infinity, then we can derive this potential representation. But you remember we really used in its proof that we have this quality of u. So for instance, we said, okay, we can really pick any direction, integrate a one-dimensional function there, use chain rules and so on. We vanish outside some compact support so that we can use there the fundamental theorem of calculus. So they really use the regularity. But now that we have this representation on a good subclass, and we also have these quantitative bounds, we can in fact extend this identity to the full H1 space. Okay? So the corollary is if u is an H1 Rn and n is at least 3, then lemma 10.3 is still valid. Yeah, so would this mean that we, for u from this class, we get the same representation as we had there for the more regular functions? Let's give a little proof of this. So what do we have here? So maybe let's just copy the pure expression. So we have ux equal to 1 over sigma n minus 1, and then this integral Rn gradient u dot x minus y over x minus y to the n minus to the n dy. Okay, and for this right hand side here, this is first of all, it's a bounded operator. Bounded operator from H1 Rn to L to upper star n. So why is this? I mean, so this is the expression that I can bound by the least potential, and gradient of u, if u is in H1, then this is in L2, and we just showed that we get a bounded mapping from this argument in L2 to something in L2 upper star. Okay, so this is boundedness of this operator. But what's somewhat important is, so this operator is defined by this expression, but for all H1 functions. It's not that we took this expression on this dense subclass CC infinity and extended it to a bound operator. No, we directly showed it defines a bounded, or it defines an object which is everywhere defined and it's bounded. Okay, so keep that in mind. So we know that this is the right hand side is a bound operator, and we know that this identity holds on a dense subclass. Okay? Identity holds on dense subclass CC infinity of Rn. Okay? Holds on a dense subclass, and bounded implies that we have, in fact, ux is equal to maybe let's write here for the right hand side shortly t of u. So this is equal to t of u almost everywhere for all u in H1 Rn. So this is just in fact more or less extension by continuity and using some arguments like, okay, if it's bounded in LP, then you get subsequences that converge almost everywhere. But now this TU operator is just the expression that we want to have. It's not just it's not a bound operator that comes from a density argument, but it's really a priori this operator is defined by this expression. So we can write here is 1 over sigma n to the minus 1 Rn gradient uy inner product x minus y over x minus y to the n dy. Okay, so this is the proof of this corollary. Then the next corollary is fairly easy. Corollary should be 10.9 now. In the beginning, there was somehow, as a motivation for the Reeves potential, I said, yeah, well, if I take this representation back then for the C or for the complexly supported functions and apply absolute values, and I get domination by the Reeves potential. Now I have this representation for all H1 functions, so I also get this domination. Okay, so n is again strictly larger than 3, so that I can use the previous corollary. U is an H1 of Rn. Then this gives me that u of x is dominated by 1 over sigma n minus 1. Here I can directly write the Reeves potential applied to the absolute value of the gradient of u evaluated in x. Okay, so this is a corollary that doesn't need a proof, I hope. And now the next corollary, I said we will have a lot of corollaries in the last minutes. So this is now actually a Sobolev embedding, but somehow now we can perform this heuristic that we had right from the beginning, where we said, okay, we want to dominate U by Reeves potential. We need mapping properties of the Reeves potential, and then it will give us Sobolev embeddings. Okay, so here I can write n larger than 3, U is again in H1 of Rn. Then I have the estimate, maybe we can make it explicit, so there's a constant C which depends on n and p, and then I will have the estimate U in P upper star norm is controlled by this constant C times the gradient U in P norm. So this is really a direct consequence of this bound here and the Hardy-Littlewood-Sobolev inequality. And we somehow use all the time that if n is strictly larger than 3, then we can apply these results if p is equal to 2. Okay, so what was the last what I wanted to say? So another point about sharpness. So I somehow discussed why for the Hardy-Littlewood-Sobolev inequality we cannot allow the endpoints p is equal to 1 and p is equal to n from the proof. But so in the lecture notes you will get some indications either by an exercise that is not posed as an exercise and also by an actual exercise that neither the Hardy-Littlewood-Sobolev inequality extends to these endpoint cases nor the embedding. So maybe I make it as a remark without number. Lecture notes plus exercise. Embedding plus Hardy-Littlewood-Sobolev. Long word. Really fail. Fail in critical case. Okay, and then we have a last theorem for today, but we won't prove it. It's an exercise for you to prove, but it's somehow you could ask, okay, this critical case, is it good for anything? I mean, I just told you, yeah, there everything fails and so on, but there's really some form of a sharp estimate that holds in the critical case, and this I will write you down as the last point on the menu for today. So this is theorem 10.11. the Gagliardo-Nirenberg inequality. Gagliardo-Nirenberg inequality. What does it tell? So here we can really include this critical dimension 2. We can take some Q which is larger than 2 and strictly less than 2 upper star. So this is interesting in the critical case. So when you work in dimension 2, for instance, then we formally set 2 upper star to infinity. So this result would really apply for all Qs up to but excluded to infinity. And here you get the estimate that U in the Q norm is controlled by, so here again, depending on dimension and Q, by it's an interpolation inequality of a product type. So I have as one factor the L2 norm of U times some exponent, 1 plus n over Q minus n over 2, and the second factor is the gradient of U in L2 norm over n over 2 minus n over Q. Okay, so you really see here that so because it's in this product form, it's still a sharp inequality. So it's not that you take here some Q which is strictly smaller than your 2 upper star, and on the right hand side you need the same control as before. So really, if you make this Q smaller, then this power here will also be smaller. So in this sense, it's a sharp inequality that would also respect these scaling inequalities. So from the scaling point of view, it's a sharp estimate, but it's of a product or interpolation type. Okay, so this the proof, it's for me the most easy proof today. It's exercise 10.4, and I really trust in you guys, so can make a QED mark here, and then I guess I would stop with today's lecture if there are no questions remaining. This seems not to be the case, so then thank you very much for being with me, and then we will see each other on Wednesday and discuss in the second part Poincare type inequalities.